All right, we got discussion 1-2 up and ready for us. This discussion or mini topic is all about scientific measurement, which is what we're going to be using throughout the remainder of the year in order to, get the things that we need to get, take measurements, do labs, discoveries, whatnot. So it is a pretty foundational start off to the year. So when we are thinking about the observations that we make, we can think about them in two different ways. We can think about them as a qualitative measurement. So qualitative is based on the quality of the substance. When we are thinking of the quality of a substance, we are thinking about things that can be measured with the five senses, and it describes the quality of the substance. So whether something is red, whether it smells, whether it's cold, that all describes the quality of that substance. Okay, so we want to get a kind of an equal spread of both qualitative and quantitative measurements. Quantitative, like quantity, revolves around numbers. Okay? So if you have 5 of something, 5 Alka-Seltzer tablets, okay? It all revolves around measurements that use numbers. So whether it is length or mass or quantity or density or anything that revolves with numbers. Okay, so that's quantitative versus qualitative observations. So we want to make sure as we go through this class that we make qualitative scientific measurements. There are 3 important things that are needed in order for this to occur. Okay? When we take a scientific measurement, probably one of the most important things is the value itself. Okay? Is it 3.14? Is it 5.7? Etc. Okay? Then we have the ability to represent the measurement device. So what do we know based on using that measurement device? Ultimately, we want to list all the digits that we are certain of. Plus one uncertain digit. So we go one place past what we know. Okay. The last thing, and I'll kind of explain more of this one in a few slides or so. Okay. The last thing we want are units. Okay. So eventually, the 3 things that I'll tell you in class, value, sig figs, significant figures, and units. Those are the 3 things that are expected of you every time we are taking scientific measurements. When you are looking at the instrument that we're using, we want to figure out what the smallest division of measurement is on the ruler. So if we are using a metric ruler, the smallest division is 0.01. You can measure every millimeter. For a graduated cylinder, it's that 10th place. The 25 milliliter graduated cylinder is measured off in 0.2. 50 milliliter graduated cylinder has 1 milliliter. So if you want units on these, this is what I'm talking about. Ruler, 0.01 liters. And 100 milliliter graduated cylinder is also marked off by 1 milliliters, and the 500 is marked off every 5. Okay? So these correct measurements came from your discovery itself. So since you haven't taken notes, or maybe you have, if you have taken them, go ahead and double check your work and make sure you have rounded to the right area, because we want to go to what we know and one place past it. So I'll do an example of that in a little bit. So a couple of slides ago, I talked about we write what we know, and we go one place to past what we know to represent the uncertainty. Okay. So what I have for you is a little demo. I have a beaker and a graduated cylinder. So I have this little 100 milliliter beaker, okay? And I'm holding it where you can see that it's 40 milliliters of water, okay? So if I were to measure out this water, I would think I have 40 milliliters. I'm gonna go ahead and pour this into my graduated cylinder. And I'm gonna see how much water I really have. As you can see, here is the 40 milliliter mark. Where are we? We're at 38 millimeters. So what does this tell you about the accuracy of measuring things in a beaker? Which one is more accurate? Graduated cylinder is greater than the accuracy of the beaker. So what this shows you is that it's important to use the correct measuring device. Okay. 40 milliliters in the beaker was actually 38 milliliters in the grad cylinder. We want to always use graduated cylinders to measure out our volumes because they are more accurate. They are higher in accuracy. They are more precise in their measurement. Therefore, we always want to use those. Okay? So that's your little demo. The uncertainty is the fact that with our digits, the only thing we know is the 40 milliliter mark. Okay? We only know the tens. Whereas in our graduated cylinder, we know every milliliter. So the uncertainty is greater in the beaker than it is in the graduated cylinder because we just don't know, which is bad. All right, so I just touched on precision and accuracy. Now we're going to get to talk about really what those two things are. Okay? So a lot of times we use these interchangeably. However, they do mean two very different things. So when we're talking about the precision of data, we are talking about how close your data is to each other. So if we were playing a game of darts, okay, here's my dartboard. If you didn't know what that was, there's the dartboard. Okay. When we are talking about precision, if we were to throw darts and all of them landed right in the same area, that would be a precise measurement. Accuracy represents how close your data is to an actual value. How close data is to the actual value. So in this, maybe you're comparing it to an average. That's probably the most common thing you'll compare it to. But if we go back to our dart thing, my lovely dartboard, here we go again, and I would draw these pictures, okay? Accuracy means that we want to get that bullseye, okay? Even if you hit the points out here, if you hit this bullseye at least once, your data is accurate. Okay? So if something is both accurate and precise on our bullseye, we would be right here. All of your data is around that bullseye area, okay? That's accurate. This is precise. And all of that is when we are comparing our data. So unfortunately, in real life, sometimes data isn't always what we want it to be, okay? This is not an opportunity for us to be like, well, we suck, okay? It's an opportunity for us to figure out why our data isn't what we thought it would be, okay? So a lot of times how we do that is through our percent error. And what percent error does is it compares the actual value, what you're supposed to get, minus the experimental value, which is what you actually get, divided by the actual. And what that does is it just gives us a percentage, once you multiply by 100, that tells us how close our data was to what we were supposed to get. It also depends on what instrument you're using. Okay. And this goes back to our demo. Do you think the error in a beaker is greater or less than the error of a measurement made with a graduated cylinder? Error is greater with the beaker because there's more uncertainty. There is not as little of increments that it's broken up to. There's a lot of wiggle room. Okay? So when we're talking about this, for something to be accurate, it must be within the range of plus or minus the certainty. So the last known measurement value. Okay. So that means half above and 1/2 of that certainty measure below. Okay. What do I mean by this? If we were to take this graduated cylinder, we talked earlier about how it is broken up into 1 milliliter increments. Okay? This is our certainty. What your measurement device is broken up into is your certainty. So then, in order to figure out what is accurate, we can be within a range of 0.5 milliliters below to 0.5 milliliters above. Took me a little bit to actually spell that. They have to be within 1 milliliter of each other, okay? So for that specific example that we just talked about, precision would be within, so if your measuring device is still 1 milliliter, that's your certainty. They have to be within 1 milliliter of each other, so or the certainty of each other. Okay, so you could go a milliliter above or below or within each other. Okay, so measurements, if we still had to get 2.7, if you got 2.7, 3.7, and 1.7, all of those would still be precise. They're relatively close to each other and within that certainty. Okay, so let's do an example. If we were using a 100 milliliter graduated cylinder and we measured those values, but the average value we're supposed to get is 80 milliliters, would we be accurate, precise, or both? So the first question you have to ask yourself is, what is your certainty? Okay, so in this case, anytime we take a measurement, we always go one place past the certainty. That's our uncertain value. From the previous slide, we said 100 milliliter beakers are measured off in 1 milliliter. Well, every milliliter is our certainty. Okay, notice how we kept this 0.0. If this is our certain value, so we know that these are counted off, okay, we always go one place past that certain and include that decimal point, okay? This value is always estimated. Why we do this, a lot of people always ask me this, why we do this, is because science is uncertain. There is always things that could go wrong, so in order for us to account for that, we always choose an estimated value after that, okay? So when we are thinking about the certainty, so our certainty represents our 1 milliliter, okay? So in order for us to be accurate, we have to be within plus or minus the certainty. So all of our values have to be within 0.5 milliliters below to 0.5 milliliters above. And that is compared to so when we're talking about the accuracy, if we're trying to figure out if it's accurate, when we compare it to our average, which is what we're trying to get here, are all of our values within 0.5 of 80? The answer is no. It's not accurate. You have 82, 79, 78. It's not within 0.5. Okay, so not accurate. What about precision? Are all of our values within 1 milliliter of each other? No. So remember that precision is within your certainty of each other. And your accuracy is plus or minus your certainty from your average value. So is the student accurate or precise? No, neither. So now on to everybody's favorite thing, sig figs. Okay. First of all, what are sig figs? Significant figures. I call them sig figs. Nice and short. Okay. If you see SF on your paper or on your Canvas comments, that's what sig figs are. Okay. What sig figs are a measurement that includes all certain digits plus one estimated digit. Often we see sig figs in calculations. And that just comes from when we take measurements and accounting for that uncertainty that arises. And some rules with sig figs. Okay. All non-zero numbers are significant, always. Always significant. Zeros have some rules, which we'll talk about in the other slide or the next slide. So how do we know if a zero is a significant figure or not? Here we go. Okay. Captive zeros, so zeros that are in between two non-zero numbers, are always significant. Okay. So if I were to ask you how many sig figs are in this number, we have 1, 2, 3, 4 total significant figures. Because non-zero numbers are always significant, and this rule tells us that zeros caught in between them are always significant. How many sig figs is this? 3. Okay. So captive zeros are always significant. Then we come to leading zeros. Leading zeros are to the left of non-zero numbers or decimal points. So these 3 zeros are not significant. The 2, and the 1 give you a total of 3 significant figures. What about this one? I hope you said 3. Remember, leading zeros are not significant, so you have 1, 2, 3, because this is a captive zero. Lastly, trailing zeros are not significant unless there is a decimal in the number. So these are to the right of non-zero numbers or decimal points. So if we look at this one, this has 2 trailing zeros, but there's no decimal point. So we only have 1 significant figure, which is the 5. We put that decimal place on there. Now we are in this kind of caveat. So they are not significant unless there's a decimal point. So now putting this decimal point here, it makes this significant as well as those 2 zeros. So that gives you a total of 3. Now try this one. Remember that leading zeros are never significant. Trailing zeros are significant when there's that decimal point. So this gives us 2 sig figs. Then we have some rules for multiplication and division. For multiplication and division, I think is the easier one because you apply the least number of sig figs between the numbers that you are using. Okay, so look at these. How many sig figs is this? How many sig figs is this? I hope you said 3 and 2. So when we divide these 2 together, we want to keep only 2 sig figs. So go ahead and grab out your calculator and type that in. You should get an answer of 894.6. Okay. But because we only want to keep 2 sig figs, apply the least number of sig figs, then our answer would be rounded to 890. Your exponents do not count for sig figs. Exponents do not count. For addition and subtraction, you always round to the least number of decimal places. So if you look at here, we have 3 decimal places versus 1, 2, 3, 4, 5 decimal places. So when you add those two together, you get 0.0, 0.1024. We only want to round to that third decimal place, so that would be rounded 2.102. So that's for addition and subtraction. And then we get to multiple steps. So you want to do your order of operations, so PEMDAS, taking it back to your algebra days. Okay. You want to work your way through it, so do this step first. Get that subtraction happening. Apply rules at each step. Then move on to the second one. Okay. So when we do 568.99 minus 232.1, we get 336.89, which is unrounded. How many decimal places do we want to keep? Because it's addition or subtraction. This is going to round to 336.9. Remember your rounding rules. Anything above 5 goes up. Anything below 5 goes down. 5 goes up. Okay. Then we take this 336.9 divided by 6.5, and you get 51.83 for addition and multiplication and division. We want to keep the lowest number of sig figs total, so we're going to go ahead and round that to 52, and that would be your final answer. So that is discussion 1-2. Let me know if you have any questions.